Uh, okay, so and this time we are very glad and honored to have Dr. Eunshin Byon from University of Michigan to give us a talk about digital twin calibration with big data. So just before Dr. Byon starts the talk, let me just give you a brief intro for Dr. Eunshin Byon. She's a professor and Richard Wilson Scholar in the Department of Industrial and Operations Engineering at University of Michigan. She earned her PhD in Industrial and Systems Engineering from Texas A&M University in 2010. Dr. Byon's research interests encompass data science, quality and reliability engineering, and system informatics and uncertainty quantification. She served as a chair for QSR of Informs in 2019. Dr. Byon's research has been supported by NSF and various industry partners. Her research team has received multiple Best Paper awards from QSR and data mining of Informs, and IISE transactions and various subdivisions of IISE annual conference, including the DAYS, simulation and energy systems. So currently, Dr. Byon is a department editor for IISE transactions and a senior editor for Informs Journal on data science. Her previous editorial role includes serving as associate editor for IISE transactions, Informs Journal on data science, and IEEE transactions on TASE. Let's just welcome Dr. Byon and enjoy the topic about digital twin calibration with big data. Yeah, Dr. Byon, please.
Thank you very much, Dr. Wang, for your kind introduction. And I'm very honored and happy to present my research on the QSR webinar series. So let me share my screen. So everybody can see my screen?
Yeah, I can see it.
Thank you. Okay, so I'm going to present my recent research on the digital twin calibration with big data. So digital twin is the big jargon these days. Digital twin is a virtual representation of physical process or system as a real-time digital compartment. So this is a set of mathematical functions that simulate the behavior of real-world system. So in my perspective, digital twin is not really new, but it has been there. But it becomes much more popular these days because of the advances in numerical algorithms and computing power. So these advances bring digital twins to the forefront of operational analysis and management of many applications. And it has been widely used in several applications, including wind power systems, building energy systems, electric vehicles, and other applications. So let me give you some example of digital twins. So let's take a look at the wind power cyber physical systems. So here in the upper right corner, you can see the layout of a wind farm, which is in Indiana in the United States. So the blue represents turbines, wind turbines, and red represent the meteorology tower that collects the meteorological conditions. And if we zoom in each turbine, then in the right corner, you can see the anatomy of turbine. You see the blades, and after the blades, there is a nacelle that includes gearbox, generator, and many control systems and sensors. So this upper part represent the physical system, and we have cyber systems or the digital twin model that simulates this physical system. So there is this wind farm level digital twin that represents the operation of multiple turbines in a wind farm. And there is also digital twin that simulates the operation of each turbine or even each subsystem inside the turbine. Another application is building energy application. Building energy consumption consists of about 75% of the US electricity use. So analyzing building energy consumption behavior becomes really essential for building design and operations. And in response, some organizations, such as the National Renewable Energy Laboratory of Department of Energy, they developed a physics-based building energy model, shortly BEM, that simulates the building energy operations. So there could be many different digital twins, and this research focuses on the parameter calibration in digital twins. So, there could be different types of digital twins. Some digital twins are constructed purely based on data-driven approaches like machine learning models or deep learning models. Other digital twins are developed based on physics-based first principles. And in this research, we focus on this physics-based digital twins. And in these digital twins, oftentimes we need to set the parameters a priori to run the digital twin model. So if you look at this picture in the bottom, there is this actual system or process like a wind farm or actual building. And there's this input, oftentimes operating condition, and there's output. So we have this physical process or physical system. And we have digital twin that simulates this physical system that takes the same input to generate the output. And in this digital twin, in addition to the input, which is operating condition, many times we have to specify the parameters. And these parameters also influence the output of the digital twin computer model. So we want to calibrate these parameters so that the simulated output can be close to the system output or the actual output. So this is the parameter calibration. Just to give you some example, let's take a look at the wind power system. So in the wind farm with multiple turbines, performance of wind turbines are not independent, but they are subject to interactions among turbines known as wake effects. So here you can see these turbines we call upstream turbines. And when wind blows from south to north, then these upstream turbines, the blade rotation of upstream turbines generates this additional turbulence. And this is called wake effects. So the wake effects stands for the recirculation of wind flow behind wind turbines. And this wake effect affects the performance in the downstream turbines. So the upstream turbines absorb the kinetic energy from wind flow. So the downstream turbines generates less power compared to the upstream turbines. And to represent these wake effects, many computer models have been developed. For example, CFD model or fluid dynamics model have been developed, but CFD model is very computationally demanding. So researchers also develop a simplified engineering model. And one of the most popular model and fundamental model is called the Jensen's wake model. And this Jensen's wake model can be viewed as the digital twin of this wind farm operation. What it does is it estimates the wind condition at the downstream turbine. So for example, let's look at this figure. Here, the x-axis is the downstream distance. So suppose there is a wind turbine here. This is the upstream wind turbine. And when a turbine is located in this area, inside this wake region, then we call downstream turbine. And the performance of this downstream turbine is influenced by the upstream turbine. And the influence is dependent on the distance between upstream turbine and downstream turbine. So we have this distance. And this influence is characterized by the wind speed that the downstream turbine faces. So V1 is the wind speed at the downstream turbine, and V0 is the wind speed at the upstream turbine, and V1 is smaller than V0 because of this wake effect. And here, this factor is called the wind speed deficit. And this wind speed deficit is influenced by some factors like the distance, but also there's this parameter theta, wake decay coefficient. And this depending on this theta, V1 value can vary. There are other parameters like CT, the thrust coefficient. Usually CT is given by the wind turbine manufacturer, so it's known, but theta is the unknown. There are some parameter values, default parameter values suggested in the literature and also in the wind industry. For example, 0.04 for offshore wind farms. But when I use these default values, I didn't really get good result from the Jensen's model compared to the actual data. So this means we have to calibrate this data so Jensen's wake model can be really the distal twin of the actual wind farm. So this is the parameter calibration. We want to calibrate this data such that Jensen's wake model can generate accurate output compared to the actual data. So the problem can be simply formulated as this equation, very simple. So here we have n data points from actual system, like a wind farm, and L is a loss function, and Y is the observed data from physical system, so the data from wind farm, for example, and Xi, this is the input, so like this is the operating condition, like wind speed and turbulence intensity and other environmental factors. And eta, this is the distal twin output, at Xi, same input, and also the theta, for example, the wake decay coefficient. So we want to find theta that can minimize the difference between actual data, actual output, system output, and distal twin output. So the problem itself can be quite simple. And this formulation has been used in other machine learning problems, like simple linear regression, or in the deep learning. We use this loss function to to estimate the parameters. But the difference is here, this distal twin output, eta, this doesn't take any closed form because this is the output from the computer model. So we treat this eta as the black box. So to evaluate eta at one data point, so like X and theta, we have to run simulation. So it takes time. And when you have large data points, let's say when capital N equals 50,000 data points, then, to evaluate this eta 50,000 times, it takes a lot of computational efforts. For example, let's say running simulation at one data point takes 2 seconds, then this is now really computationally heavy simulation model or distal twin model. Still, it takes 28 hours to evaluate this loss function at one theta. So this can be quite computationally heavy. So then other challenges is, in the wind farm wake model, we only have one parameter. But depending on application, we could have multiple parameters. For example, in the building energy model, we have like 30 parameters. So some distal twins involve multi-dimensional or even high-dimensional parameters. Then how does this problem be addressed? So this problem has been studied in the literature. Parameter calibration has been studied. And the most widely adopted approach is an emulator-based approach or surrogate-based approach. And among them, Bayesian calibration is the most widely used approach. And Bayesian calibration uses this linkage function to link the distal twin output with the real observation through this linear model. And recently, frequentist approach has been also proposed to handle some limitations of Bayesian approach. And it also tried to minimize the difference between real observation and distal twin. And in these approaches, the common theme is they construct the emulator for this era, the distal twin, the response surface, and also for real observation. So, to construct these surrogates, what they do is they pre-design the design points, X and theta. So here, the design point is the input of distal twin computer model and also input of physical experiments. So they choose design points X and theta a priori, where to run simulation model, where to run physical trials. So they fixed these design points, for example, through the Latin hypercube design or other design of experiments methods can be used. So they fixed the design points a priori, and then they collect data at those fixed design points. So they collect data from physical process. They can do physical experiments, and they run computer experiments to obtain the response from the distal twin model. Okay. And then once they collect data, they build emulator for Y and eta, and then they find theta. So these approaches are suitable when data is scarce. So when the computer experiments takes time, so for example, running simulation to get one data point takes weeks, then you cannot really run simulation 100 times, right? And also when the physical trials are limited, then the data we cannot really enjoy big data. So when the data is scarce, this emulator-based approach is good, is suitable. But the problem is, they fix the design points a priori before having any understanding of the system structure like Y and eta. So they don't utilize the information of the system output. System output, when I say system output, this is the output from physical system and also the digital twin. So they generate the data first, and once they generate the data, then they calibrate. So the data generation and calibration are separated. And when pre-selected design points are not really informative, then maybe the calibration accuracy is not very good. So this traditional setting is good when running simulation or when conducting physical trial takes time. So when the data scarce is good. However, in the digital twin setting, we may not have this scarce data, but maybe we can enjoy big data because usually digital twins is not really computationally heavy. So the time need to run digital twins can be on the scale of seconds or minutes. So we can get some number of data points from digital twins. And also oftentimes the big operational data from physical system or physical process is available. So when you have this rich data, instead of building surrogate model for parameter calibration, our strategy is to take active learning and active sampling ideas. So we want to selectively choose the most informative data points sequentially or adaptively to improve the calibration performance in terms of both efficiency and accuracy. And to this end, we devise an adaptive and sequential design of experiments that exploits the problem structure. So just to give some idea, so here, let's say this is the parameter space we need to explore. And this is the operational data set from physical process. So for example, we have data from wind farm, and each data points, X is the weather condition and Y is wind power generation. So we have kept the N data points. And for parameter calibration, we take the iterative approach that exploits the system structure. So suppose the current incumbent is theta I, then at theta I, we choose the most informative data. So for example, you can choose this blue data points, the subset of data points. And at this design point, we run simulation to obtain the system output, the output from the digital twin. And with this information, we move to theta I plus 1. And at theta I plus 1, we also collect another data points, informative data points to run simulation to get theta I plus 1. And we proceed until some termination criteria is satisfied. So in this approach, the design points, theta I, and also the X value are selected adaptively. So theta I's are decided on the fly, and we draw samples that best guide the calibration procedure. So data generation and calibration are not separate, but seamlessly integrated. So this is the overarching idea of digital twin calibration with big data. And under this overarching framework, I'm going to present two research topics. The first one is the parameter calibration with stratified sampling, which is motivated by wind power systems. And then I will move on to the next topic. So again, we consider this wake effects in wind energy, and we use this Jensen's wake model. And our goal is to calibrate the wake decay coefficient. Later, we used more advanced wake model, but in this presentation, I will use Jensen's wake model to discuss the idea. Again, we want to find theta, the wake decay coefficient, then minimize this empirical loss to quantify the difference between the actual output and the digital twin output. And eta is a complicated function of input and the parameter theta, which is often nonlinear. And to decide the decide the design point, which means where to run the simulation model or the computer model, we use gradient descent optimization and also stratified sampling. So let me explain this in more detail. So gradient descent, I guess all of you know gradient descent. We studied this in the nonlinear optimization class, right? So gradient descent is one of the common methods in nonlinear optimization, and it iteratively updates the incumbent. So here we have loss at each xj. So we have the n data points, and we can run simulation at each xj to compute the empirical loss, okay? And we need to compute the gradient at each data point xj. And but because this error is the output from computer model, this is we don't have closed form of the gradient for error. So we approximate the gradient by taking the finite difference. So we run simulation at theta I plus h and theta I minus h, and then we take the difference. And we do this for every data points and take the average of the gradient, negative average of the gradient to get the updating direction. And then our next design point for the parameter will be theta I plus some step size times the updating direction. So this is the gradient descent. So this is good. However, the problem is when you have large number of data, this can be computationally demanding because at each data point xj, we have to run simulation to get error. And we have to run simulation to get error at theta I plus h and theta I minus h. So when you have n data points, we have to run simulation 3 times n times, which is really computationally heavy, even though running simulation at 1 data point doesn't take really time. So instead of using gradient descent, we can use stochastic gradient descent or batch stochastic gradient descent. So the idea is simple. So instead of running simulation at all data points, we can choose data points randomly. So we have a subset of data points of size n, small n, which is much smaller than the original data size. And we run simulation at this subset of data points to get the updating direction. So in this SGD has been used in many machine learning models like deep learning, so which is good. However, the problem is when we choose the data randomly, we will have noise estimation of the gradient. We studied this in the central limit theorem, right? So when the gradient is very noisy, then our convergence will be slow. So here, let's say gradient L, this is the true gradient, okay? But we choose the data randomly, okay? So our empirical gradient could be very different from the true gradient. So in this case, maybe we can, our convergence in SGD procedure takes time. So if you look at this graph, this is one of the experiments. And the red is the trajectory of the theta when we use SGD to calibrate the parameter. So you can see that this parameter starts at 5 and it quickly converts to around 2, which is good. So if you look at the red trajectory, but after it converges, it goes up and down. And that's because this sample gradient is highly variable. Because the variance is large, sometimes it goes up, sometimes it goes down. And it takes time until the convergence. So we want to reduce the variance of this sample gradient to reduce the number of iterations. So we can we can calibrate the parameter in a more computationally efficient way. So to reduce the variance, we employ variance reduction technique. There are several variance reduction techniques, and here we use stratified sampling. So in original SGD, from the big data with capital N data points, we randomly draw the sample, okay, and then we run simulation. But in the stratified sampling, we first divide the input space, okay? So we divide the input space, we partition the input space, and at each input space and each partition, we draw samples, okay? And this partition is called stratum. And the idea is if some strata are more important, then we draw more samples from here. So suppose P1 is the influential stratum, then we draw more sample from P1 compared to other strata. Okay, so this is the idea of stratified sampling. So in the stratified sampling, the gradient is computed this way. So we compute the gradient at the kth stratum, kth area, kth partition. And the gradient at the kth partition is, suppose we draw nk samples from that kth stratum, then at each data points, we get the sample gradient, and then we take the average. Okay, so this is the kth stratum gradient. And then pk is the proportion of data at the kth stratum. Then we take the, add up all these pk times the kth stratum gradient. And this gradient is biased estimation of the gradient. So the idea is by allocating more budget on the important strata, important partitions, we want to reduce the variance. So in the original SGD, the empirical gradient could vary a lot. But if we use the SSGD, stratified SGD smartly, then we can reduce the variance. So the empirical gradient could be close to the true gradient. So we can reduce the number of iterations in the SGD procedure. So here, this is one of the examples. So previously, this red, it takes time until convergence. But when we use the stratified sampling, because we were able to reduce the variance, it converges quite quickly compared to this red case. Then how can we reduce the variance? So we want to reduce the variance of gradient. And in fact, previous researchers, they said gradient, empirical gradient, transpose, and true gradient measures how well the direction of sample gradient is aligned with the true gradient. So we basically minimize the variance of the gradient direction. Okay? So we minimize the gradient direction, and this can be expressed as this equation. And here, the decision variables are important. So the decision variables, we have number of strata. Okay, so how many partitions do we need, and how to stratify, how to partition. So the stratification structure we call omega k. Okay. So to get the partitioning structure, stratification structure, we need to decide the partitioning variable and their splitting locations and resource allocation. So we have 3 different types of decision variables. So here, the important thing is really the stratification structure. This is preliminary results. And we try stratification with different input variables. First, in wind energy system, in the wind powered system, wind speed is the most important variable. So I first tried wind speed to divide the input space with 4 strata, okay? But the average number of iterations was 33, and this is not much better than original SGD. So I looked at the problem and I tried different input variable, which is the turbulence intensity. Turbulence intensity measures the stability of wind conditions. So maybe it's related to the variance of the gradient. So I tried turbulence intensity, and unexpectedly, turbulence intensity, when I used turbulence intensity, I was able to reduce the number of iterations and number of evaluations remarkably. So compared to 33, I only need 6 iterations until convergence, compared to 7,000 evaluations, which means when I use wind speed, I have to run simulation 7,000 times. I have to run this sequence 7,000 times. But when I use turbulence intensity, I only need to run simulation 1,000 times. So this really indicates that the stratification structure is really important. If I use both TI and WS, it also reduces the number of evaluations and iterations and evaluation compared to wind speed. Okay. So we need to really decide how to divide the input space to implement the stratified sampling, but it has not been studied thoroughly in the literature. So again, our problem is given fixed budget n at each iteration, which means the size of the subset data points, our goal is to find the strata size and stratification structure and budget allocation to minimize the variance of the gradient direction. Okay, and here the budget allocation is relatively easy to solve when we use the Lagrangian multiplier. The optimal budget allocation is proportional to pk sigma k. So if we plug this to the original objective function, we get this. Okay, so our optimization formulation can be reduced to this. So we need to minimize summation over k, pk times sigma k. Okay, so we need to decide the number of strata and the stratification structure. And this objective function tells us that to minimize this, we need to minimize sigma k. So sigma k, this is the standard deviation of gradient direction at the kth stratum. So this means sigma k is the within stratum variability of the gradient. Okay, so if we can reduce or minimize within stratum variability, we can achieve the minimum variance. Then how can we do that? So suppose we have single variable, okay? So our input is just one variable. Then we want to find the breaking points to define the stratification structure. So this is the first stratum, second stratum, third, so on and so forth, okay? So when k is given, given k, to define the optimal breaking points, we were able to derive the condition. So if this condition is met, then we can find the optimal breaking points. And this result is the result for univariate problem. So when you have a single variable in the input space. But extending this to multivariate problem is not very straightforward. And also in practice, it's not really implementable. So for multivariate problem, we used decision tree idea to get the stratification structure. So decision tree, I guess in this community, many of you already know the CART, classification and regression tree, right? So it divides the input space with a variable. In this figure, we divide with x1 first, and then x2 and x1. So we divide the input space recursively so that the terminal nodes could have homogeneous data points, right? Then, once we have these terminal nodes, then these terminal nodes correspond to the strata in the stratification structure. So we employ this decision tree idea. So we recursively grow a tree by identifying the most effective splitting stratum. So when you have multiple nodes, we choose the node that gives us the largest variance reduction. And at each node, we need to decide the splitting variable, like whether we need to break with x1 or x2, and also where to break, okay? So we need to decide all these, and we do this recursively that gives the greatest variance reduction. And the important part is, suppose this is the node we want to break, okay? And we need to decide the breaking variable, x1, x2, or x3. And at each xi, we need to decide the breaking points. And to decide the breaking points, we use the result from this univariate analysis. Okay? So we apply this univariate analysis result at each node to decide the breaking points. And we choose the node and breaking variable and then breaking points that can reduce the variance the most. So, for example, this is the result from INFARM case study. In the first iteration, when theta was 0.5, this was the stratification structure based on this binary tree construction. But as we iterate with this SGD, the stratification structure changes. So when theta was in the fifth iteration, when theta becomes 0.1, we have different stratified stratification structure. So overall, at each theta, we partitioned the input domain by constructing this binary tree. And in the binary tree, to get the splitting point, we use this result from the univariate analysis. And once we partition the input domain, we decide the sample size, the NJ, the budget allocation, and then draw NJ samples from the operational data. And then we run simulation, the discipline computer model to get error. Okay? And then we compute the gradient of the loss function and update theta. And we proceed this iteratively until some convergence criteria is satisfied. So overall, going back to the overarching scheme, so we have parameter space and we have observational data. And we update theta I based on the gradient descent or stochastic gradient descent adaptively. So our procedure takes this active learning approach. So we don't fix the design point a priori, but we update theta I on the fly during the calibration procedure. And also we take the active sampling approach that best guide the calibration procedure. So at each theta I, to choose the data points, we use the stratified sampling, and we optimize the stratification structure. So we draw the samples that can best guide the calibration procedure. And this active learning and active sampling, they are integrated together. Okay, and we have some convergence analysis, but I will skip the details for the sake of our time. And we apply this procedure to the actual data collected from wind farms. This is the data from inland wind farm with 40 turbines, and we use 1,659 data points, and we use 70% of this as a training set and 30% of this as a testing set, and we conduct 100 experiments. And this is the result. So compared to SGD, when we use this stratified SGD, we were able to reduce the iterations from 12.5 to 9.6. And number of samples, this is the number of evaluations. Basically, how many times we run simulation, we were able to reduce the number of evaluations. And we also extended this SGD to ASGD. So ASGD is the adaptive SGD. This one is, instead of using the fixed size at each iteration, it increased the data size until some criteria is satisfied. And in this case, we use the coefficient of variation. So there's typo. So when the coefficient of variation, which is 0.9, then we, until the coefficient of variation, which is 0.9, we increase the data size at each iteration. So ASGD use 4 iterations, and it used 12,000 times, 12,000 runs until the convergence. But when we employ stratified sampling in addition to the adaptive SGD, we were able to reduce the number of evaluations by about half. Okay, so we were able to reduce the computational efforts remarkably compared to the SGD and ASGD. We also compare the accuracy with Bayesian approach. We consider 2 Bayesian calibration depending on how we set the prior. And you can see that in using the numeric example, and these examples are taken from the literature with different problem structure. And as you can see, this our approach, SSGD, really generates estimates close to the true value, but Bayesian approaches sometimes deviate from the true values. Okay, so this is the first project, and I will move on to the second project. And I guess we can take questions after I finish the presentation. Okay. So the second project is the explainable parameter calibration. This is motivated by the building energy systems calibration. So in the building energy system, we have building energy model, the discipline model, and the input is the temperature, wind speed, solar radiation, and humidity. Okay, and with this input, we can run simulation to get the energy consumption of a building. But in addition to this input, there's a parameter. And in the wind power system, we have one parameter, rate decay coefficient. But in the building energy model, we have like 30 parameters. Okay, So when you have this large number of parameters, calibration is not very easy. Okay. So previously we used GD, SGD, but SGD requires a substantial number of simulations because with n batch size and k parameters, we have to run simulations 3 times n times k times. So it takes time. So this time, with this high-dimensional parameter space, we decide to use the Bayesian optimization. And I believe in this community, most of you know Bayesian optimization, so I will skip the detailed discussion. But basically, what BO does is to minimize or maximize, depending on the problem context, minimize the objective function, and it constructs a probabilistic model for F, the objective function, for example, using Gaussian process, and it finds the next design point, so basically where to run simulation next time, through acquisition function. And this acquisition function considers the uncertainty of their estimation. So usually you choose the design point that where the uncertainty is high, and also where the predicted response is low, because our objective function is the minimization function. Okay. So when we have many parameters, okay, so the capital D is the dimension of input variables. So when you have many parameters, still BO suffers, BO has several challenges. Basically, number of design points to construct the Gaussian process grows, and maximizing local likelihood for GP hyperparameter becomes difficult, and optimizing the acquisition function becomes more complex. So these first 3 bullet points are well-known challenges in high-dimensional BO, but we also find another interesting problem. So the acquisition function in BO has to search the boundaries of the parameter space in the early iterations, because in these boundary data points, uncertainty is high. So for example, here, this is the design points when D equals 1, 2, 3, and green is prior design points, and we want to decide the next design point. And in BO, in early iterations, it has to choose the next design points in the boundary. For example, here, or in this boundary, or in this boundary, because the uncertainty is really high in these boundary data points. So that's kind of natural, right? Because in BO, uncertainty matters. However, the problem in this parameter calibration using distant twins is that oftentimes these boundary values generate very abnormal, unrealistic output patterns. So for example, in the BEM, building energy model, when cooling supply airflow rate is close to 0 and 1, then this is rate, so it should be between 0 and 1, and 0 and 1 are feasible values. But when this parameter is close to 0 or 1, this distant twin generates very strange outputs. So in the first 3 figures, A, B, C, the red is the simulation output when this parameter value is close to 0 or 1. And black is the actual data, okay, actual energy consumption. And this red simulation output is so different from the actual consumption, and it's just unreasonable, okay? However, when this parameter is between 0 and 1, then the distant twin control model generates reasonable outputs, okay? So we have this misspecification problem when the design points were close to the boundary values. But the thing is, in this calibration problem with the large number of parameters have oftentimes different contributions. Most parameters have no or little effect, which is called effect sparsity or parsimonious principle. So the response could often be dominantly influenced by a small subset of parameters. Okay? So the important parameters, not all the parameters are important, but some. Okay? And even those important parameters have different importance level. So some parameters are more important, other parameters are less important, and some parameters are not really influential. It doesn't really influence the output of the digital twin model. So our goals, we have two goals. First of all, of course, we want to improve the calibration accuracy and efficiency. And second goal is to identify those important parameters and explain the importance of those parameters. So explain of AI. And to achieve these goals, our idea is to build Gaussian process surrogate in BO using reduced dimensional parameters. Okay? So instead of building Gaussian process in the original dimension, capital D, we want to choose important parameters, and we want to build the GP in the reduced dimension, small d, okay? And why is that? We want to construct more accurate GP surrogate, and we want to strike a better balance between exploration and exploitation, and we want to quantify the importance of each parameter. So we slice the original dimension. Basically, we reduce the original dimension stochastically to fit Gaussian process. Okay, so in the beginning, we don't have any idea. So let's say we just choose the first five parameters. Okay, and we calibrate this. But then we have some idea. So next time we choose different parameters, and here the darker, the more important. So in the second iteration, we may choose theta 1, theta d, theta 6, which are important parameters. Okay, and as iteration proceed, we choose important parameters only. Okay, so this is the idea. Okay, so then how to choose these parameters, important parameters? How can you run parameter importance? So we set the weight vector for each parameter. So pi I is the importance of parameter I. Okay, so we set the weight vector, and we want to reduce the parameter dimension stochastically. So we build a preference distribution for this weight vector. And we employ multi-unbanded approach to update the preference distribution over iterations. Okay, so first we construct the Gaussian process, and we get the sensitivity measure. There could be different ways to get the sensitivity measure. In this study, we use the Sobel sensitivity analysis. Okay, so we get the sensitivity index for parameter K. And we use this index as the new data points for the K parameter. And we use this T and K as the reward in the multi-unbanded framework. Okay? So suppose that each parameter weights follows Gaussian distribution like this with prior, then the idea is we want to update the posterior distribution with this reward. Okay? So the idea is the more sensitive parameter, we want to increase the weight. Okay? We want to increase the posterior mean of the weight so that this important parameter can be selected in the next iteration. So this is the overall idea. And this is a result from the BEM, Building Energy Model case study. And you can see that we consider 30 parameters, but here the gray, this is the trajectory of the posterior mean of the weight vector. And you can see that about 22 parameters are not really important, and only 8 parameters are important. And among these 8 parameters, this theta A, this is the most influential, and other 7 parameters are somewhat influential. And this black, this theta A, this is the cooling supply airflow rate. And in the previous slide, we see that when this parameter was close to 0 or 1, we have misspecified result, right? But when we reduce the dimension, we didn't really have that kind of problems. So overall, we choose small d parameters out of original capital D parameters according to the preference distribution from the using the multi-unbanded framework. And we construct GP with this small d selective parameters to choose the next design points. And we design the next point for other remaining parameters. And we run simulation, and we collect additional data, and we do this iteratively. And we call our approach as the explainable sliced calibration, so X sliced calibration. We have some regret analysis to get the upper bound of the average regret, but I will skip the detail. we apply this approach using the numerical example. We consider 3 examples. All examples have very complicated problem structure. And the original parameter has 30 dimension, but we only use 2 or 3 important parameters. So the true important parameters are either 2 or 3 in these examples. And here is the parameter importance trajectory. In example 1, theta 1 and theta 2 are more important. It turns out that theta 1 and theta 2 are more important than other parameters. And it aligns with this true important parameter dimension. And here, in this left bottom figure, it measures the parameter importance. So the red is the parameter importance measure from our approach, and the blue is the true parameter importance. And you can see that our estimated parameter importance is similar to the true importance. And because of that, we were able to distinguish these two parameters compared to the other unimportant parameters. And we also observe similar patterns in other examples. And we compare our approach with other BO. Okay, we consider 3 approaches. The first one is the random sliced design. This also randomly select a subset of parameters. So it reduces the parameters, but it doesn't quantify the importance. And full design, this is the original plain BO without slicing the parameter space into 2 subspaces. And trust region-based BO, this is also another approach that handles high-dimensional BO problem. And it doesn't reduce the parameter space, but what it does is it restricts the search space around the current incumbent. And this one also has been proposed in the literature to address the high-dimensional BO challenges. So this is the result in these 3 examples. And in all cases, our MSE was much smaller than other competing algorithms. And our parameter value, calibrated parameter value, was close to the true parameters. So we got pretty good, promising results. We also apply our approach to the building energy model calibration. We use energy plus building energy model developed by Department of Energy's National Renewable Energy Laboratory area. And we use actual data collected from a building in Austin. And here, this is the comparison of MSE of our approach. And red is the trajectory of our MSE over the BO evaluations, and other trajectories are from competing algorithms. And you can see that we were able to reduce MSE in any number of evaluations over other approaches. We also compare the performance with the L2 calibration, which is the frequentist approach, and also Bayesian calibration. And in this BM case study, and we were able to get much smaller MSE in both training and testing sets. All right, so in summary, the advancement of digital twins open up new research opportunities in a variety of application sectors. However, big data still pose several challenges, including how to handle large computation when you have a large number of data points, how to handle high-dimensional parameters with the unknown parameter importance, how to handle complex structure. So for the sake of time, I only presented 2 projects, but I have another project that has the hierarchical parameter structure. So when we have these kind of challenges, we find that instead of using the previous previous approach that used the surrogate model, if we use this active learning and active sampling, we can achieve better efficiency and also accuracy. So our approach judiciously choose the design points to adaptively run simulations, which show advantage to address these challenges. And in the future, we want to extend our approach to handle other calibration issues, including dynamic calibration, when the parameter values change over time. And functional calibration, when primary values depend on other input vectors, and also multi-dimensional objective case. And in the end, once we calibrate the parameters in digital twin, we want to use digital twins for optimize our decisions, right? So we want to connect with decision making. So for example, in the wind energy, we can use this well-calibrated digital twin model to decide the yaw angle or the turbine direction for wake steering control. And in building energy model, we can use this digital twin to optimize the demand response program. Right. Yeah. Thank you very much for your attention, and I will be happy to answer any questions if you have.
Yes, thank you very much, Dr. Byon. I think this is very intriguing and fruitful work. Yeah. So let's see. Do we have a question from audience? So please feel free to unmute yourself. Maybe yeah, actually, so let me take the icebreaker. I actually have two questions, each one for your each work. For the first work, I actually interested in using the decision tree to split the areas or the parameter space. So in your example, actually, you show the case when the parameter space is rectangular. So I think this definitely works well. But what if the parameter space is in a irregular shape? Do you think this decision tree strategy still works?
That's very good question. So yeah, so we only consider the hyperrectangular decision space. But if the parameter space is not rectangular, then maybe we can consider some like a mapping of the input space. So maybe I guess we need some modification of this approach. And
I
there's
see. Okay. Yeah. Thank you. And the second question for the second work, I think this is more like a clarification question. So you mean you use Sober's index to indicate the importance of the parameter. So in this case, do you think do your method still needs to run through all the dimension of parameters first?
Right. Yeah. That's a really good question. So yeah, so to get the sober index, we construct the GP over the original space. Yeah.
Okay.
So yeah, because we need right. So yeah. So this approach will be can be applied when capital D, the original parameter space is like 2030. But I know if the original dimension is very large, let's say 50, 100, then maybe this sober index itself is not really accurate, right? So in that case, maybe we have to consider like a double stochastic dimension. Yeah, so basically this approach is developed based on the problem where the capital D is around 20 to 30. But when we have a larger D, okay, of course the sober index may not be very accurate. So to address this, we have this stochastic selection. So instead, so let's say based on sober index, we sort the importance. Then instead of choosing the highest small d parameters, we use this multi-unbounded to explore the parameter space. So to address the weakness of the sober index or any sensitivity index. So every parameter has a chance to be selected.
I see. So essentially, you constrain the being selected to do this sensitivity analysis as another layer.
Right.
Then you can constrain for like some affordable computational time or affordable computational resource in calculating this sensitivity index. Okay. Yeah, that's I think a smart strategy. Yeah, thank you. I think that's all my question.
Very good question.
Thanks. Yeah, let's see. Do we have a question from audience?
Yes, I have a question if you let me.
Yeah, please.
Thank you so much. Thank you, Professor, for your presentation. The research was really interesting. And could you please go back to slide 16?
This one?
Here, thank you so much. Yeah, here you mentioned that you selected the most informative the observations or data points from your data set, right? Could you please explain a little how did you do that and what was your approach?
Right. So here, in the first problem, they use stratified sampling. Okay.
Right.
So if we do not use the stratified sampling, just use SGD, we just randomly draw samples. So we just randomly draw black samples, right? But in the stratified sampling, we divide the design input space, right? And we draw samples from important strata. We draw more samples from influential strata. So that way we can choose the subset of data points that are really influential, which means here influential means they can reduce the variance of the gradient.
Okay. Yeah.
Yeah. So we can achieve like computational efficiency.
More accuracy, right? Thank you so much.
Yeah. Great question.
Do you have more questions from the audience? Yeah, if no, let's just thank our speaker, Dr. Eunshin Byon. Yeah, thank you very much. Very, very interesting talk. Yeah.
Thank you.
Yeah.
Thank you for organizing this
Yeah.
message.
Thank you. And thank you for all the audience. Thank you.
Thank you. Bye.
Yeah, bye-bye.